The purpose of this presentation is to show the process of a muscle contraction from start to finish, as well as explaining the different types of muscle contractions and how they'd be used in a sporting context. Here is a brief overview as to how a muscle contracts. To begin with, the stimulus within the environment must be recognized by the sensory nerves. Then, if sufficient stimulus has been detected, an impulse is sent through the central nervous system and peripheral nervous system in order to generate an action potential. There is then the issue of the neuromuscular junction, a synapse or gap that lies between the motor neuron and muscle fiber. The impulse needs to reach the muscle fiber but is unable to travel across the neuromuscular junction as there is nothing there. Instead, neurotransmitters must be sent across in order for the impulse to continue its journey. The next stage is the actual contraction of the muscle, which happens through a process called the sliding filament theory. An easier way to understand this process is with a sporting example. So, if you were to take a goalkeeper, then their stimulus would be a ball coming towards them. Their senses, which in this case will predominantly be their eyes, will recognise the stimulus, and the sensory neurons will deliver the sensory input into the brain. The brain then makes a decision as to what it wants to do and will send instructions to the motor neurons, which will cause the muscles to contract and perform the skill, which in this case will be the goalkeeper diving to save the ball. The first stage of the sliding filament theory is the nerve impulse. After deciding on the appropriate action, the brain will send a signal down through the nerve until it reaches the synapse at the neuromuscular junction. The impulse is unable to get across the synapse in the same way that it travelled down the nerve, and so it needs to find an alternative way to do so. In order for the impulse to reach the muscle fibre, it needs to travel across the synapse at the neuromuscular junction. For this to happen, the chemical ACH travels across the synapse in vesicles until it reaches the receptor sites located at the postsynaptic membrane of the muscle fibre. This is more commonly known as neurotransmitters. If enough ACH is sent across the synapse to the receptor site, then the impulse is able to carry on. It will then travel along the muscle fibres and down the T-tubules until it gets to the sarcoplasmic reticulum. This is the place where the calcium ions are stored. Once reaching the sarcoplasmic reticulum, the impulses cause the calcium to be released. There are two important proteins that are used in the process of a muscle contraction. These are called the actin and myosin, the actin being thinner in appearance when compared to the myosin. Both of these proteins must work together to allow muscle contraction. Located on the actin is the actin binding site. This is the point at which the myosin and actin will bind during a muscle contraction. However, when at rest, two proteins called the troponin and tropomyosin are covering the actin binding site and preventing any contractions. The tropomyosin is a long thin protein that wraps around the actin, covering the actin binding site, whilst the troponin is a globular protein attached to the tropomyosin to help hold it in place. Meanwhile, the myosin is hydrolyzed whilst the muscle is at rest, waiting for the opportunity to bind with the actin and cause a muscle contraction. The reason the myosin is energized is because of the bonds within the ATP being broken down and therefore releasing energy which the myosin will use during the contraction. In order for a muscle to contract, the myosin and actin must bind together. In order for this to happen, the myosin arms need to have access to the actin binding site. However, the tropomyosin and troponin are in the way. In order to overcome this, the troponin and tropomyosin needs to be moved out of the way and make way for the binding of the two proteins. This is where the calcium mentioned earlier comes in. The calcium that was earlier mentioned attaches itself to the troponin, which changes its shapes and displaces the tropomyosin and reveals the actin binding site. The energized myosin arm will then take this opportunity to bind with the actin binding site, creating a cross bridge. Once this has happened, the myosin will pull the actin towards the M line, located in the middle of the sarcomere, which consequently causes the Z lines to move towards each other, which results in the muscle shortening and contracting. This creates a sliding motion and is where the phrase sliding filament theory comes from. In order for the myosin arm to relax and detach from the actin binding site again, it will require more ATP. In order for a muscle to sustain a contraction, it will require lots of ATP to allow the myosin arm to repeatedly bind and detach from the actin binding site. In addition to this, nerve impulses will need to be sustained from the brain to the sarcoplasmic reticulum to ensure that calcium ions are still being released and preventing the actin binding site from being covered by the troponin and tropomyosin, which leads me on to my next point, being that access to the binding site must be sustained in order for the myosin arm to be able to bind. In order for a contraction to end, the impulse being sent from the brain to the sarcoplasmic reticulum needs to stop. This will stop the release of calcium ions, which will mean that the troponin and tropomyosin will return back to its original shape and position, where it will once again cover up the actin binding site and prevent any more cross bridges between the actin and myosin from being formed, which will therefore end the muscle contraction. There are 4 different types of muscle contractions, some of which we are more familiar with than others. These contractions are concentric, eccentric, isometric, and isokinetic. Concentric and eccentric contractions are both forms of isotonic contractions, meaning that the length of the muscle changes whilst the tension remains the same until relaxation. A concentric contraction involves the muscle shortening as the ends of the muscle come closer together. This type of contraction is what the majority of people would be able to identify as a contraction as opposed to the other types. An obvious example of concentric contraction would be the contraction of the biceps brachii during the upwards phase of a bicep curl. An eccentric contraction is similar to the concentric contraction in the fact that the muscle is changing its length whilst contracting. However, in the case of an eccentric contraction, the muscle is lengthening as opposed to shortening. An example of an eccentric contraction would be the biceps brachii lengthening during the downwards phase of a bicep curl. Isometric contractions involve the muscle not changing in length at all while still producing a large amount of force. Typically, isometric contractions are used to sustain posture, although a more obvious example of an isometric contraction would be the plank. The abdominal muscles are contracting in order to stabilize the body, however no movement is occurring and the muscles are neither lengthening or shortening. Isokinetic contractions are not often used naturally. Instead, they are typically used as a form of rehabilitation by physiotherapists. An isokinetic contraction involves the muscle contracting at the same speed on both the upwards and downwards phase of the movement. This is achieved by using an isokinetic dynamometer, which counteracts the force being put on it by a person in order to maintain one consistent speed.